This video training segment, RFID Technology Part 1, covers RFID frequencies and tags. The RFID is the next generation of data capture, and the initial portion of the data capture is the RFID tag, which is attached on goods or assets or people, and is read by antennas and readers, RFID antennas and readers, which passes the data and brings value to the existing applications across all industries, going from manufacturing to retail as well as other business functions. The bird's eye view of RFID is that we start with an inlay, which is an asset or locator that is attached to the object or person to be tracked. We have the data encoding or capture, which is a function of a printer encoder that prints on tags as well as encodes them, or standard reader interrogators, which can both read and write data to the tags. Once the data is captured, it is then passed through the standard IT data networks into your application systems and eventually into usable data for the people. The key point here is that RFID includes the asset identifier and the data encoding and the data capture. From that point on, the data is passed through standard IT networks and environments. So RFID focuses on the asset identifier and locator and the data encoding capture technologies. Now within RFID, we have 5 frequency ranges or bands that are used. We have what is low frequency, which is 125 to 134 kilohertz. We have high frequency, which is at 13.5 megahertz. We have active tags, which function at 433 megahertz. We have UHF, or ultra-high frequencies, which is in a frequency range of 860 to 960 megahertz. And then we have the microwave, which is the 2.4 or 5.8 gigahertz. Why do we have different frequencies? The RFID uses the frequencies based on government regulations. Governments will specify what frequencies can be used in what countries, what power levels can be used, all of which we'll talk about in the standards and regulations section. But also the host material. Different frequencies react differently around metal and water, which can be problematic for some frequencies. The read range, if you want to read a millimeter or two on a credit card versus you want to read 50 feet or 500 feet, will help determine which frequencies you can use, and also the speed of data transfer. As a general rule, the lower the frequency, the greater the speed of data transfer, and also the greater amount of data that you can transfer. This is a goods frequency summary chart, and to point out some of the highlights, the low frequency, once again, has low data read speeds and small amounts of data. You're only looking at 16 bits of data. The read ranges are short, 3 to 5 feet, and the common usages are for access control, animal tagging, but it can be used in other cases, but these are the most common usages. High frequency has a medium read range, a medium read speed. This is what's used on your credit cards and also your access cards when you're trying to get into buildings. They have generally short read ranges up to about 3 feet. And common usages, once again, are smart cards, credit cards, and proximity cards and vicinity cards. And we're going to talk about proximity and vicinity when we're talking about the protocols and the regulations and standards in subsequent videos. VHF, a very high frequency, is for active tags, and this is the frequencies at which the active tag itself transmits. You have high read speeds and you get large amount of data. You have the read range up to 1,000 feet under ideal conditions, and common usages are asset tracking, locationing, container tracking, fleet tracking, those types of things. And then we have the ultra-high frequency, which is the most common in the United States, which gives us high read speeds, small to medium amounts of data, and it's used for pallet case level tracking, part of the DoD mandate. And this is, once again, a frequency range. And the microwave, which has high read speeds, medium amount of data, read ranges up to 300 feet, and it has been used for container, rail car, auto toll roads, pallet level tracking. However, microwave is used very infrequently because it's an unlicensed frequency, and there are many other devices that are out there, your cordless phones, for example, all of which cause a significant amount of interference, which is unpredictable in the work environment. So you rarely are you going to see microwave used within the standard RFID world. So the RFID total system, first we have, of course, the tags, and we have labels, which can be printed on or not, as well as we have the inlay, which is the core of the RFID tags, can also be encapsulated into a much harder material, which can then go through laundries, can go through autoclaves, can go through very severe weather conditions, etc. So you have the tags, then you have the readers, and attached to all the readers, obviously, you need an antenna. But the readers can read the tag and or write to tags, and they're also called interrogators. So if you see the word interrogators, it just means reader. They can read and write data. And then when you go into the software, the data is first passed into what's called middleware. And the middleware has the responsibility of the function of converting the data from the binary or hexadecimal form in which it comes from the readers into a usable form, into EBCDIC or ASCII or some form that can be used by the rest of the system. Middleware also does other functions, and once again, this is covered in a subsequent video. So the components of the RFID technology system. Remember, RFID is just the tags and the readers, but other elements that are required to get the data, move the data, act on the data, etc. So the total components can include tags and readers, sensors, Wi-Fi if you're transmitting the data via Wi-Fi, networking if you're using Cat5 or any of the standard Ethernet cabling. You have the software like middleware. You have databases because the data that we do get after you've converted it gets stored into databases. You have the internet. The data can be sent up through the cloud or back from the cloud. And then, of course, most important of all of this is your business process management, because your business processes are those things that are going to actually use the data, make sense of the data, and turn raw data into information. So that completes the frequency section of this video. So next we're going to talk about RFID tags and labels. Now RFID tags can be categorized in several different ways. First is according to power source. The passive tags, which are the standard ones that you see most times, receive power from the reader. And what this means is that those tags in and of themselves are inert. They have to be put in the presence of a reader. The reader sends out an RF signal. That signal is captured by the antenna on the tag, which creates power to power the chip, and that same wave is reflected back off of the antenna back to the reader, and this establishes the communication link. So now you can send data out to the tag and have the tag respond with data coming back. If we took that same passive tag and we put a battery in with it, then we would have a semi-passive tag. And the reason why we would do this would be if you wanted to attach sensors, you need to have some way to power the sensors. So if you had heat, temperature, heat sensors, temperature sensors, gas sensors, etc. You could attach a sensor to the semi-passive tags and write the data on the semi-passive tag because you have the power on the tag itself. However, semi-passive tags still need a reader be able to read the data that has been captured and or to write data back to it in terms of being a standard passive tag. The active tags have their own antennas, have their own power supply, and can read, and they have the transmitter, and so they can read and write and transmit data all fully within themselves independently. Another way to categorize RFID tags is by frequency. Any given frequency requires its own unique tag design, and so we have low frequency tags, high frequency tags, very high frequency tags, UHF tags, and microwave tags. And also, remember, the core of the RFID tag is the inlay itself, and so we can encapsulate that inlay into many, many different forms and the form factors, and that's so we can put it into labels, into wristbands, into buttons. We can put it into laundry tags, etc. So by form factor. So these are the most common ways of categorizing or classifying RFID tags. So now we're going to talk about each of the different tag types. So the passive is a device made up of an integrated circuit, has an antenna integrated all into one. The integrated circuit has memory to store data and some processing logic to be able to communicate with the reader. The key thing here is that these are memory chips on the tags. There's no application processing, so you can't tell it to add 1 and 1 and get 2. You can't have it encrypt data. The tag itself do the encryption on data. So the tag is a memory chip. So you're going to write data to that tag from a reader interrogator, and you're going to receive data back from that tag. So it's a memory-only tag. So the memory, usually we can specify the amount of memory that we want on a tag when we order the tag, but generally we only put what's called a unique serial number that's written onto the tag that identifies the object or the person to which the tag is attached. And this serial number is sometimes called a license plate. And when you read that license plate, that gives you the key to get into your databases where all the data is stored. We have read-write tags. All the tags following the current Class 1 Gen 2 V2 standards can be written to up to 10,000 times. So that's all part of the standards. Or you can, in fact, have the factory pre-program or pre-write all the tags for you, of course, for a cost. So your decision as to which way you want to go. And optionally, the data on the tag can be locked so that it can't be changed, and the data can also be password protected in the memory so that it would require a password to be able to read the tag or write to the tag. The integrated circuit, the chip that is on the tag, is a microprocessor. Once again, it's a memory chip with 40 to 50,000 transistors for our passive Class 1 Gen 2 tags. It's memory only to store data. It receives data from the RF wave. It's captured by the antenna and modulates. Modulate simply means to change. Modulates. The backscatter is the term that's used for the reflected wave that comes. Remember, the reader is sending out an RF. The antenna catches that RF, powers the chip, and reflects the wave back. That is called backscatter. So it modulates or changes the backscatter RF waves to communicate with the reader. So that's how they communicate. You have a strap which connects the antenna to the chip. You have the antenna, which obviously takes up most of the chip, and you have the substrate, which is the material which holds all of the antenna, the IC, the straps, everything together. So it's the plastic backing for the inlay. And from a term point of view, if you have just an inlay, then that's called an inlay. If you put adhesive on the back of it, then it's called a wet inlay versus a dry inlay. And so you can't have adhesive attached directly to the inlay. So an example of a high frequency HF RFID inlay tag, you showed that it has the coils of the antenna, and all HF tags will have a coil antenna that looks something similar to this. That may be circular, it may be rectangular, it may be square, but it will be continuous loops of the antenna. You see the chip in the middle that's attached. You have the straps that or sometimes also called the interconnect that connects the antenna to the chip. And of course that's sitting on the substrate. Now on UHF, because it's a different frequency, we have a different tag design, antenna design. And so what you see here is that you have the chip in the middle, you have the straps, as you can see in the enlargement there, you have on the substrate, and in this case, if you look at the antenna, there are two identical antennas or mirror imaged antennas on either side of the chip. And this type of antenna is called a dipole, D-I-P-O-L-E, a dipole antenna, because it has two poles to it. So this is what a UHF RFID inlay looks like. So the passive tag antennas typically consume most of the tag area. The design varies by frequency. As we saw, the HF has the continuous circle loops, whereas the UHF has a dipole. The low frequency has a ferrite core, metal core, with a wire wrapped around it, multi-turn coil on a ferrite core. And this most commonly you will see used in animals, and if you've gone to the vet and had your dog or cat had a chip put in, this is what they would have. It would be an encapsulated chip that is low frequency. The high frequency, as we just saw, has the 3 to 9 turn planar spiral. In other words, the antenna has a continuous loop going around the outside. And with the UHF, once again, there are a variety of configurations, but they're virtually all of them are going to be dipole. There are a few exceptions, as you can see, with a mirror image antenna on either side of the chip. And the two elements to discuss here is one is the length. If you added up the length of the antenna on either side, it'll be about half the wavelength of the half the wavelength in this case of UHF, which is 33 centimeters. So each side, if you measured all that out, you'd get about 15 centimeters as far as the antenna length goes. And you'll also see different antenna designs based upon the material to which the inlay is going to be attached. And we'll see that in more in a few minutes here. And then the last, we have the microwave antenna, which is half the wavelength, which is 6 centimeters long. But once again, in the gigahertz range, rarely are we going to do anything with RFID or use RFID. So a passive tag, we've sort of thrown the words around of an inlay, a tag, and a label. The inlay is the core. That is the substrate. That's what we just saw, the substrate, the chip, the straps, the interconnects, the antennas. And that inlay, if we put that inlay inside of, encapsulate that inlay in a hard material, then we're going to call it a tag. All the functionality is exactly the same. It's just that we've encapsulated it into a harder material. If we take that same inlay and sandwich it between or under paper, and we can now print on that paper, then that's called a smart label. Once again, the functionality from an RFID point of view is exactly the same. It's just they're just different form factors of the exact same thing. So the key here is that whether we talk about an inlay, a tag, or a label, functionally we're talking they all function exactly the same way. So we encapsulated passive tags, you can encapsulate into RF-friendly material. Not all plastics are RF-friendly. If you remember not too many years ago when you were recycling plastic bottles, you could recycle some plastic bottles, but you couldn't recycle other plastic bottles because they were made, in this case, oil-based versus water-based. So the same thing is true with all plastics. So if you're going to be working with different plastics, you need to make sure that the plastics are RF-friendly. And then the encapsulated tag may be used to, you can put it on whatever you want to. They have them, you can put it into laundry tags so they can go through the laundry. You can put them into autoclave encapsulation so they can go through autoclaves, high temperature, etc. Also, if you're going to put a tag onto a metal, as we talked earlier, that there are issues with metal and UHF. If you're dealing with UHF, you want to be able to need to encapsulate the tags or get the tags so that they are built specifically to work on metal. And some of the materials used for encapsulation, and these are some of the more common ones. There are others, but these are the more common ones. Now, all passive and semi-passive tags, whether it's UHF or HF or LF, employ a unique communication system to avoid the need for a transmitter contained in a low-cost tag. So instead of transmitting its own signal, the tag couples with or couples to the signal transmitted by the reader. And as a result, by varying the coupling, the tag communicates without transmitting. So it means that we're going to change some element within the transmission. For UHF, that's going to be the amplitude. So we're going to change the amplitude, and by changing the amplitude of the wave, we'll be able to send data. And remember that all communication, everything within RFID is in binary, zeros and ones. So we either have a 1 or we have a 0. And so the analogy is if you're using a tiltable mirror to reflect a flashlight, you could flash it and hold it for a period of time, and it would be you could say that's a 1, or you could hold it for a shorter period of time, and that would be a 0. So all communication all happens in zeros and ones in binary in RFID. So within the RFID, we have two distinct ways in which the readers communicate with the tags. For the low frequency and high frequency, we have what's called near field or inductive coupling. And within this, within the UHF and microwave, we have what's called far field or passive backscatter. And we're going to talk about each of these independently. So low frequency and high frequency use near field or inductive coupling. Used for short read ranges up to 2 feet. More commonly, for example, on your credit cards, they have, based on the protocol, they're only going to read 1 millimeter, or if you're using an access card going in and out of a building, you'll notice that you have to get pretty close to that access card. So that's used for short read ranges. The HF antennas are not directional. What this means is that we're actually creating, with LF and HF, we're actually creating a magnetic field. And a magnetic field is a circular, and so it fills an area. It's not directional. When we talk about UHF, we're going to talk about sending out an actual radio wave that can be pointed in a given direction. But for LF and HF, we're creating a magnetic field. So any tag that goes into that magnetic field, which are roughly spherical, can then be read. The readers are generally less expensive. Several antennas can be easily multiplexed to one reader, and the key to that statement is that when we talk about UHF readers, we're going to talk about having multiple readers connected directly to the UHF antenna. Within HF, we can actually only have one antenna connection. However, we can put a multiplexer in front of that, and to that multiplexer, we can then attach a number of HF antennas. So that's why that's an important statement. It's easy to read objects with water and aqueous solutions. This is important with UHF, which we're going to find. UHF is absorbed by water, so UHF cannot read through water, cannot read through the human body, cannot read generally through your hand if your hand is covering a UHF chip. So HF, on the other hand, is very good through water. It's a magnetic field, so it goes through water and other material without any problems. Good for smart shelves. A smart shelf is think of a cabinet that has a drug cabinet, medical cabinet, and that medical cabinet has a variety of vials or containers on it. If the shelf itself is an antenna, then as you can read that antenna, so you know if someone puts a vial or container back onto that shelf, or if they take someone off that shelf, you can now read that tag movement in or on or off that shelf. And so that's what are called smart shelves, also used in retail stores where they have stacks of inventory and they're trying to keep track of what inventory is on each shelf. Lowered read distances provide more secure reading. If you can only read 1 millimeter or 2 millimeters or up to maximum 2 feet, if you want to intercept that communication, you have to get within that read range to be able to read it, which if you're with credit cards, for example, which use HF, have a read range of a few millimeters, you'd have to get within a few millimeters of that credit card with another reader to be able to read that particular credit card. So you have greater security with HF and LF than you would with UHF. So near field inductive coupling. I don't know how many of you back in the school days remember that you created a magnet and you had a power supply, a battery, you had a wire that you wrapped around an iron nail, and when you connected the battery and it went through the coil, it created a magnet. The nail became a magnet. So following that same concept, if you create the magnetic field and now you put a tag in it which has a coiled wire on it, if you remember all the HF inlays have the coiled antennas, if you put that coil antenna inside the magnetic field, then that will create power, which will power the chip and give you the communication means. So that's called inductive coupling, where you have the reader creates, through the antenna, creates a magnetic field, and then the antenna from the tag is introduced into that, and now you can read the tag. So that's called inductive coupling. You'll also hear it called near field coupling. And once again, with HF, you have the coils on the antenna, and that's because you're dealing with a magnetic field, and those coils going into that magnetic field generate power. On switching to UHF, ultra high frequency, we have far field or passive backscatter communication. You have read distances of approximately 50 feet. Some new vendors can read a little bit farther, some a little bit shorter based upon the application and a variety of other things. But anyway, so you have a long read distance. It's a directional antenna, so it's putting out a beam that you can focus in one direction, as opposed to HF where you had the a spherical magnetic field. It's difficult to use with objects containing water or aqueous solutions. Once again, UHF is absorbed by water. And the frequency bands and max power levels are subject to country regulation and differ by per country to country basis. What this means is that when UHF came along and we said we want to use UHF, we looked at each country in the United States, said we want to use the frequency range of 902 to 928 megahertz. We went to Europe and said we want to use the same, and Europe says we can't use that range because we're using 915 for our cell phones and other things within that range. So they said, well, what can you give us, Europe? So Europe came back and said we can give you 865 to 868 megahertz. And they went to each country around the world, and each country set up what their frequency range was going to be. All of these frequency ranges are between 860 megahertz and 960 megahertz. So you have different frequency ranges by countries, but all within that same range. And then the different power levels, based upon the amount of power that you give to the antenna, will establish what your read range is, tied to the, obviously to the tag. But because of interference with the bands that are next to UHF, the countries have also limited or changed the power, specified the power settings for that can be used for each of the different countries. And as we mentioned, we talk about passive backscatter. So with passive backscatter, the reader sends out an RF wave. The antenna on the tag captures that RF wave and does two things. One, it excites the electrons, gives an electron flow, which is used to power the chip, and that same wave is reflected back to the reader, and now you have a full communication link from the reader on the carrier wave going out to the tag and the reflected wave coming back. So now the reader can send commands to the tag, and the tag can respond with the data, either writing the data or responding back and reading the data from the tag. And that's called passive backscatter. And down at the bottom, you'll see it says far field propagation. What that means is that the power at the tag is approximately 1 over the distance squared. So if you have the power, so that helps to establish what your read range could be, what the power coming off the reader is going to be at a given distance. So at 2 feet you have 1/4 the power, at 3 feet you have 1/9 the power, etc. And so that you can give some idea of how fast the power is going to drop, and give you some indication as to what the read ranges might be. Semi-passive tags, once again, is a passive tag, and we've put a battery, we've encapsulated it into a form factor, and we've put a battery with it. So it's also called battery-assisted passive, or BAP. This is a standard passive tag that we just talked about with a battery added. The battery powers memory, circuitry, and sensors, and you have a battery life of up to 3 to 5 years. The actual life of the battery is going to be determined by how frequently, what sensors you have tied to it, how frequently you collect data from that sensor, etc. But generally you can get 3 to 5 years. And semi-passive tags used to be smaller than active tags, but in recent years some of the active tags have been able to come down in size. But they are definitely larger than passive tags because you have a passive tag plus the battery. You can communicate up to 150 feet. It allows for sensors, GPS, temperature, gas, etc., to be attached to the tag. It obviously costs more than a passive tag. Has relatively good storage. You can get up to about 64 bytes of storage. Makes a good choice for asset tracking, reusable totes. Higher cost assets will cost anywhere from $5 to $150, but because you could use it on multiple assets, you might be able to use it 20 times or 30 times or 100 times, depending upon, because you can take it off, recode it, put it on another asset. So the per unit cost is what's important, not so much the initial cost, and can be read by most RFID readers if they are Class 1 Gen 2 compliant. There are a few specialized readers that are out there, but not very many. But it does not contain a transmitter. It uses the backscatter to communicate. Therefore, we have to have a standard passive RFID reader to be able to read the data from the tag or to write data to the tag. It does not depend on power from the reader to power the IC, and it's not as popular as active tags, so there aren't a lot of vendors out there that are making passive tags anymore. And here's some examples of different passive tags and what their common use is for. And you can go out and just Google this, you know, semi-passive RFID tags and look at all sorts of different pictures and types. Active tags have a battery and a transmitter. They typically use either the ISO 18007-2005 standard, in which case the tag is always transmitting at 433 megahertz, or you have the ISO 2009-7 standard, once again still functioning at 433 megahertz, but the -7 standard allows for some different capabilities that we'll talk about in a minute. The data rates are very high, in excess of 3,000 bytes per second, up to 128 kilobytes of user memory, so you can put a lot of memory out there if you want to. You have long read ranges. They'll advertise 1,000 feet under ideal conditions. Reasonably, you'd expect up to 300 feet to be very reliable in almost any condition. Because these are encapsulated, how you're going to mount them. You're going to rivet them to it, bolt them to it. You can put pressure-sensitive tape. You have some epoxy adhesive that you can do. Any way that you can mount these. They're larger than passive tags, once again, because you have the battery in there. You can also attach sensors to it, and the battery life is 2+ years, once again based upon use. If you're active and you set it to transmit every 10 seconds versus you tell to transmit once a day, obviously you're going to impact the battery life. Some pictures and examples of some active tags, and once again, if you want to see more of these, just go out and Google RFID active tags, and you'll see a whole variety from different vendors and different places. So this is just a few examples, and the bottom one has a few sensors attached to it. -7, active tag -7, was a specialized standard that was added to the active tags. It's an RFID active standard. Originally it was intended for asset tracking, but it operates at 433 megahertz. Now this is the frequency at which the active tag transmits. Multi-year battery life. The range up to 2 kilometers, which is, and potentially farther, is going to depend on the power in the battery and another number of other things. But it will penetrate concrete walls, water, and the ability to bend around metal objects, meaning that if a metal object's in the way, if it has an edge, it will get diverted and get bent around it and keep on going, as opposed to reflected back completely. The small, lightweight protocol stack on the chip itself minimizes the silicon cost, so the chips aren't hugely expensive. And the data transfer rates of 27 kilobits per second is a very, very high transfer rate, so you can send a lot of data very quickly. And you can attach sensors to it, and obviously you have security support for it in terms of being able to lock the data, password protect the data, all those things. The other element we have to talk about with tags is the material to which the tags are going to be attached. Now, materials, all the materials in life, if you think of light, when light hits a metal surface, what does it do? It reflects. If it hits a mirror, it reflects. If it hits water, it gets absorbed. And so we have reflection, refraction, we have absorption, and we have a dielectric effect, which is detuning. What this means is that when the RF tag is attached to a given material, that material can detune the reflected wave. Remember, we send out the carrier wave from the reader. The tag antenna reflects back the wave, called backscatter. Now, if that wave going back has to be the same frequency at which it was sent, so that the reader can get it and understand it. Some material will change the frequency enough that the reflected wave can't be recognized or read by the reader. So we have, that's the dielectric effect or detuning. Some common materials affecting performance of the tag attached to them, obviously water and aqueous liquids absorb UHF. And if you take a standard UHF tag and read it in open air, it will read fine. If you attach it to a water bottle full of water, then you won't be able to read it, possibly a very short read range, an inch or two, but you won't get the same read range that you get in open air because the water detunes the tag. And the material with high moisture also affects absorbed UHF. Walmart found out that when they left cardboard boxes sitting out on the deck in their warehouses in Houston, which is a very humid area, that after a while the cardboard absorbed enough moisture out of the air that it detuned the tags so that they couldn't read the tags anymore. And metal also reflects HF, so that and UHF, so which will cause detuning of the tag as well. So some common materials that we're talking about is we have cardboard, you have absorption and detuning, you have conductive liquids, generally aqueous liquids, carbon fiber, pastes, you have plastics, metal and foil packaging, groups of cans, human body, animals, and the different effects on it. And part of what you'll see with UHF is you'll see different antenna designs on the inlay itself. And those antenna designs and the design of the chip are built to accommodate some specific material to which they should be attached. And so if you go out, when you're looking for tags, you have to tell your vendors what materials they're going to be attached to so that they can come up with the correct tag or inlay with the correct antenna design. So that's our module today. So we talked about the technology review, and we talked about tags and labels. Thank you very much for attending. Goodbye.